In 6.1a, we talked about yesterday and I introduced exponential functions to you. We're going to review a little of the information that I gave to you yesterday.
After that's completed, then get to the new material. Let's see here. Quadratic, or in our exponential function, we've got the limitations on it. We're going to raise it some exponent or variable. Base limitations, the b must be positive, and the b equal to 1. So it can be a positive number for 1 is how you want to think of it. So look at how we evaluate a few things, and this little crowd here says evaluate f of x, okay, for x equals 3.
For various x's. These are functions, so it is going to be helpful actually if we just write them with functions.
And so this is basically asking what is the f of 3, and so that is 5 to the third power, or 125. Here I'm going to call f of x, they've got 3 to the x power, and they want us to find the f of negative 2. All right, f of negative 2. Our base here is 3 exponent negative 2. That's 1 over 3 squared, so 1/9. And then lastly, f of x equals 5 times 2 to the x, right there. We are supposed to find the f of negative 2. That's what our x value is. So that's going to be 5 times 2 to the negative 2 power, like so. When you evaluate this now, you've got to take care of exponents first. So this is 1 over 2 to the positive 2 now, which is 5 times 1/4, which is 5/4. So that's how we evaluate exponential functions. Just substitute in for the x value and then simplify your result. So let's go ahead, now that we can evaluate these functions, let's see how we can graph them relatively quickly. Now yesterday, hopefully in the lesson, if you went through the homework problems, you got to see what some of these graphs looked like. So let's go ahead and try to graph them by ourselves. So to do that, we'll just generate some points, and this is probably about enough for any of these graphs. So let's take 2 to the 0 power. That's just 1. Anything to the 0 power is 1. Then 2 to the first power is 2. 2 squared would be 4. 3 squared, and I don't know why I just did 3 squared. 2 to the third would be 8. Then 2 to the negative 1 would be 1 over 2. 2 to the negative 2 would be 1 over 2 squared, which is 1/4, etc. It's 1 over 2 cubed, which is 1/8. So let's go ahead and graph this, and you'll see how easy it is. So our first point is at 0, 1. So 0, 1 is right about there. Second point we have is 1, 2. So at 1 we're at 2 right there. And then at 2 we're at 4. So 1, 2, 4 right there. And 3, 8 right about there. Negative 1 gives us 1/2. Negative 2 gives us 1/4. Negative 3 gives us 1/8. And what you'll notice as I start to do this, even if I let it be negative 4, it's going to go to 1/16, then 1/32, then 1/64. It'll always be a fraction, and it's never going to reach 0 for a value. So we're going to get really close to the x-axis, but we are not going to touch it. And we'll just kind of smooth it in, like so. And we got that characteristic of what we call exponential. In this case, we'll call it a growth curve. Let's graph the other one. Again, we do 4 to the 0 power, but that's going to be 1, and then 4 to the first. 4 squared and 4 cubed. 4 to the negative 1, which is 1 over 4. 4 to the negative 2, which is 1 over 4 squared. And then 4 to the negative 3, that's going to give you 1 over 64. Just have to take 16 times 1 more, 4. Let's go ahead and graph these. Let's find a color that we can see a little bit better. There we go. So our first point, 0, 1. In fact, these are all going to share that point, 0, 1, because any base to the 0 power is 1. 1, 4, right here. 2, 16, just way up there. 3, I'm not even going to attempt 3. Negative 1 gives me 1/4, which is just a little bit lower. Negative 2, 1/16, and now it's ungraphable. So it gets really close again to that x-axis. This one grows a little bit steeper. And so your graph should look something like that. These functions that we just looked at, these are exponential functions. And all of our exponential functions break into 2 types. The 2 we just graphed looked like this. They were exponential growth problems. Other ones that we'll see shortly here are exponential decays. So all your exponential growth problems are all going to have this going up to the right feel for them. Some may be flatter than other ones. Exponential decays, they call them decays because they're going down, 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 down. They get really close to 0 as well, but they go down to the right. So up and to the right for exponential growth, and down to the right is exponential decay. Let's look at how we get exponential decay now. We saw our 2 growth ones. You'll notice right away this is going to be different because we've got fractions in here. And we'll see what the fractions do to our function. So a half to the 0 power is just 1, and a half to the first is just a half. Then we have to square a half. It's going to be 1 squared and 2 squared. And cube a half, so we have to cube the 1 and cube the 2. And then when we put in negative 1, this is where it works out very nicely. That negative on the whole fraction causes the entire thing to flip upside down. And then it would be to the positive 1 power, but that's just 2. And when I do a half to the negative 2, the negative flips it all upside down, and then I have to square it. That's just 2 squared over 1 squared, that's 4. And to the negative 3 power, I flip it over to get rid of the negative, making it 2 over 1. And now I have to cube them both, and that's 8. And you'll see as we start to graph it why this is a decay function. At 0, I'm at 1, so that's consistent. At 1, I'm only at a half. And at 2, I'm at a fourth, and then an eighth, which is barely above the line. Then at negative 1, I'm up here at 2, negative 2 at 4, negative 3 at 8. And so you can see this is when we have a fraction as our base, we end up getting a decaying function. So as time goes by, the function gets lower and lower and lower, it slowly decays. We'll see the same thing here with 1/4, and I'm just going to write these out really quickly rather than explain them all. And all you have to do here is you just keep taking that 4 times itself. Oops, that's a 16. Times itself one more time. I'm at 3, so I got to multiply by another 4. That's 64. And then when you do these negative exponents, you just have to flip it over and then take it to whatever the power is. So here, I would flip it over, putting a 4 on top, and when I square 4, I get 16. And 1/4 when I cube it, because I'm going to flip it over, that'd be a 4 cubed, then I'd get 64. So let's graph him in pink here. He starts at that 0, 1 again, but at 1, he's already down to 1/4. At 2, he's down to 1/16. I can't graph 1/64. -1, I'm at 4. At -2, I'm at 16. It's way up here, and I can't graph past that. So here it is, another decay function. He decays quicker though. Okay, he was 1/4. That's a smaller fraction that caused it to decay quicker. Every time you take a fourth times the fourth, that's a whole fourth that it gets shrunk by, because it gives you 1/16 at that point. So there's our this is just a slide. You don't have to really know a lot from it, but I did want to point out some of the different graphs we've had now. This is our most recent one that we did in last chapter. We didn't look a whole lot at their graphs until we were doing inverses, if you recall. And then the first ones we ever learned are y equals 2 to the x. Notice they're straight lines. X squareds, those are parabolas. And now, excuse me, comes along these exponentials, and you can see how quickly they grow. You can see there's an overlap right there between the parabola and the exponential, and it looks like the parabola might grow quicker, but if this was to keep extending out, eventually this exponential would surpass it, and it would be growing much faster. So exponentials are used quite frequently when you have a very fast increase in something. Let's look. Now, this slide has a ton of information on it, but we said, or I said, exponential functions fall into two different groups, growth or decay. Well, here's how we can tell if something is a growth function. If the b value is bigger than 1, so it doesn't have to be much bigger, 1.1 is bigger, but any number bigger than 1 will cause this function to make that upward move to the right, as you can see down here. Okay, so that's a fact we want to memorize. This is your basic function for all exponentials, and then we can shift them up, or we can slide them right, left, diagonal. We can rotate them, all depending on what we do to this base function. The y-intercept is always going to be 0, 1. We found that throughout, whether it was growth or decay. It also passes through the point 1b. So if you let x equal 1 up here, you just get whatever the base is. So if this was a 2, when you plug in 1, you'd go through 1, 2. If this is a 5, you'd go through 1, 5. The other thing that we haven't talked about yet, other than mentioning it's a line you get really close to, in this case it's the x-axis that you get really close to, and you never touch it. And any line you get close to that you do not touch is called an asymptote. So there's its definition right there. It has an equation. It is a fictitious line, but it is the line you're getting close to. In this case, the x-axis. Its equation is just y equals 0. Domain is all real numbers. You can see the lowest you get to is almost 0. I'm sorry, your x values. This thing does go forever and ever to the left and forever and ever to the right. So domain is all real numbers. Range is what I was thinking of. The lowest we get to for our range is really close to 0, and then it goes up and up forever. So we say y has to be just greater than 0. You'll never get 0 out. Exponential decay now, what we're going to do is we'll see the b value changes. And so you can kind of think, if you think back, we said the b has to be greater than 0, and it could not equal 1. So here's all the numbers that are bigger than the 1. The only numbers it leaves left over are those between 0 and 1, the fraction. So in exponential decay, the b value is between 0 and 1, and that is like 1/3, 2/3, 1/5, 8/9, any fraction. That is between 0 and 1 is your base. And if you have that base, you're going to have, and I don't know why it says exponential growth there, you're going to have exponential decay. Okay, it crosses right here at 0, 1 again. The asymptote's the same, y equals 0, gets really, really close to it. This is a parent function again. It's exponential decay though. Your y-intercept is 0, 1, passes through 1b again. The asymptote, y equals 0. Domain, you can plug any number you want into for x, but your range is again just all positive numbers. You never get below that 0, so y is greater than 0. Now, what the heck do you have to do today? One of the things you have to do today is just graph a function, okay? And then state whether it is growth or decay. So right away, we can answer whether it's growth or decay just by looking inside, looking at the base. This has a base of 2/3, and that is certainly a number between 0 and 1. And we just said if the x is that fraction between 0 and 1, you are going to be decay. So we already know this graph is doing something like this. And that's just by looking at the equation. Now let's generate just a few points to graph this guy. So I'll just make a list here. Should have given myself a little more room. And we'll just make an XY table. And we'll go 0 gives us 1. Then we'll plug in 1 and we get 2/3, just the fraction out. And we'll plug in a 2 and we'll get 4/9. All I'm doing up here is squaring 2/3. If I want to take that 2/3 to the third power, it looks like this, 2/3 to the third power. That's 8/27. So we already have a pretty good graph. It crosses at 0, 1, and it's just going down like so. But remember, it's never going to touch that x-axis. In fact, we should put a little dotted line there to say that's what we're getting close to, but we are not touching. That's an asymptote, y equals 0 right there. On the left-hand side now, some of our negative numbers. Let's plug in -1, so it's 2/3 to the -1. All that does is flip it over. And then when I do -2, and I go 2/3 to the -2, all that does is flip it over, and then you got to square it. So 9/4, -3, 2/3 to the -3 is 3/2 to the +3, 27/8. So here we go. At -1, we're at 3/2. Now that is 1.5. So -1, we're at 1.5, right about there. At -2, we're at 2.25. So -2 and 2.25, about like that. And then at -3, we're at 27/8. That's 3 and 3/8. So 3 and 3/8 at -3 would be about 1, 2, 3, and 3/8. A little short of a half. And that's enough. Just sketch in what our graph looks like. Let's do another one real quick to show you how quickly you can do these. That thing is bigger than 1, so I know I have growth. So now I'm going to make a quick table to get a few values. 0, 1, 2, 3, -1, -2, -3. Now I'm going to get out my calculator for this thing in just a minute here. But to do this, I go, all right, 2.3 to the 0 power is 1. 2.3 to the first power is 2.3. Then I'm going to have to calculate 2.3 squared on my calculator and 2.3 cubed. Then we'll have to calculate 2.3 to the -1 on our calculator, 2.3 to the -2, and lastly 2.3 to the -3. So I've got my calculator open now, and I'm just going to get these answers real quick. 2.3, and I've got to square it. So that is, oops, there we go, 5.29. And then rather than type in 2.3 cubed, I'm just going to go times 2.3 because that'll take it times another one. And that is 12.1, well, we'll just go up 12.2. Then I'm going to clear this. We got to do 2.3 to the negative 1. And that gives me 0.43. So about a half. 2.3 to the negative 2. 2.3. Gives me 0.1. We'll just call it 0.2. And then 2.3 to the negative 3. 2.3 to the negative 3.1. Close enough. You can see at this point, as soon as our decimals get ungraphable, we don't go any further. So 0, 1, that's quick to graph. 1, 2.3, and you just ballpark where that's at. 2 is at 5 something, 5.2. 3 goes up to 12. And a little bit past 12. There we go. On the left-hand side, we go negative 1 is just a little bit lower than half. At negative 2, I'm at 0.2, so just barely above it, and I'm getting really close down there. And there's my graph. So it doesn't take very long to draw these things. I'm going to throw in that asymptote. That's going to be handy later on, so we might as well get used to it. That's right at y equals 0. So let me pull up the homework here, and you'll see it really doesn't take too much. Okay. In problem number 1, they just want you to identify the base. So problem number 1, we go 2 because that's our base. Remember, the base is right below the exponent, right there. It wants us to find the f of negative 2. So f of negative 2 would be 2 to the negative 2 power, which is 1 over 2 squared, which is 1/4. So the f of negative 2 is 1/4, and therefore we can answer it is decay because that 1/4 is a number between 0 and 1. Okay, so that's the first 4 problems. And then down here, you're going to have to graph it. So just make a table. Now, if you remembered a few things, one thing is you already know 1.01. Remember, it always goes through that. Oops. So when you plug in 0 up here, it'd be 1/6 to the 0 power, which is just 1. We also know 1 and 1/6. Remember, if x is 1, then it goes through whatever the base is. So 1/6. Right there. My graph looks a little bit off. I don't like that. Then we could put 2 in there. That'd be 1 over 36. But at this point, we're getting almost impossible to graph. Let's plug in some negatives. Negative 1, I flip it over, gives me 6. Negative 1, 6 is right there. And negative 2 would flip it over and give me 36. Way off the charts. So this is a very steep decaying function. Like so. And we'll write decay next to it. Okay. So that's all you're doing for 5 and 6. That is it.